All right, we are going over the Unit 6 review, getting ready for that Unit 6 quiz. So number 1 has a whole bunch of terms that you need to know. So what is the solvent? That's the thing something is dissolving in. So we'll call it the dissolving substance. The most popular solvent is water. Okay, also there's usually more of this than the thing that you're trying to dissolve. So it's also called the majority substance in solution. Okay, versus solute is the thing that gets dissolved. So the dissolved substance, in other words. It's also known as the minority substance because there's less of it. So again, if I throw salt in some water, salt is the solute, the water is the solvent. And a solution is a solute dissolved in a solvent, also known as a homogeneous mixture. It's the same throughout. Mixture. Aqueous means something that's dissolved in water. Something that's soluble means it dissolves. Something that is insoluble, it does not dissolve in a liquid. And then let's make sure you've mastered the difference between homogeneous and heterogeneous. If you mix some rocks with water, that would be heterogeneous. It's different throughout. If you scoop into that water, you might hit just water, you might hit a rock. If you mix sugar with water, that would be homogeneous. The sugar is evenly distributed throughout the water. Same thing with AlCl3, aluminum chloride. That is salt. So it would be homogeneous. Oil in water, oil is less dense, so it floats at the top of the water. That would be heterogeneous. What are 4 factors that speed up a reaction and why? 1 is heat, and that's because the solvent molecules speed up with heat, energy added. And they collide with the solute more often and with more force. Therefore, when things collide more, they tend to react more. They reach that activation energy point where the atoms can come apart, the bonds break, and then new bonds form. Another factor that can speed up a reaction is a catalyst. This is a chemical that lowers the activation energy of a reaction. Okay, so again, picture that energy diagram. It lowers this initial hump right here. So it makes it so you can take a shortcut across. Another thing that affects the rate of a reaction is concentration. An increase in the amount of solute in an area increases the chances for collisions between reactants, right? If there's more stuff in the solvent, of course it's going to react faster because there's more solute in there for it to react with. Finally, surface area. So this would be like my example that I talk about in class, crushing up a salt cube or a sugar cube before you throw it into the swimming pool. An increase in surface area, I'm going to short it SA, means more opportunity for the reactants to collide and react. So even though dissolving is an example that I gave, that's not a reaction. Dissolving is a physical change. It's ions that are separating. It's still similar in that when there's more opportunity for those reactants to come in contact with each other, they'll react faster. Number 4, what is concentration? It's the number of moles of solute in a solvent. Okay, usually you measure it in moles per liter. So molarity is also shorted with just a capital M. That's moles per liter. So here's a dilute solution. We'll call that a liter. That's 4 moles per liter. And here is a much more concentrated picture. Let's see, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We'll say that that's 19 molar of whatever I'm working with here. So this is more molecules in the same volume. That's what more concentrated means. So this one is the dilute one in comparison. Which concentration of a solution is made by dissolving? What is the concentration that's made when you dissolve 30 grams of MgCl2 in 500 milliliters of water? Well, in order to calculate concentration, we need moles per liter. So first, I need to get this into liters. So I'm going to divide by 1,000. That's going to be 0.5 liters. I need to get grams of MgCl2 into moles. So I need to add up the molar mass. So I'm going to look at my periodic table and add up 1 magnesium plus 2 chlorines. That adds to 95.21 grams in 1 mole. I only have 30 grams, so I don't even have a whole mole. I've got a fraction of a mole, 0.3151 moles per 0.5 liters. That's a concentration of 0.63 molar MgCl2. There, I calculated the exact concentration. Number 7. How many moles of solute do I have in 800 milliliters? I know I'm going to need to get that into 8 liters. So I've got 0.8 liters, and my solution has 2.5 moles of solute per 1 liter. So if I multiply these together, my units are going to cancel out for liters, and I'm going to be left with moles, which is exactly what I want. 0.8 times 2.5 is 2 moles. I'll have 2 moles of solute in that much of that concentration of solution. Number 8. How many grams of salt do you need to make 50 liters of salt water with a concentration of 0.65 molar? By the way, that's roughly the concentration of salt in the Pacific Ocean. Cool. Added a little context there. Snuck it in. All right. 0.65 moles per liter times 50 liters. How many moles is that per liter, or in that amount of water? That's 32.5 moles of NaCl. Now, I need to figure out how many grams is that. So 32.5 moles of NaCl. 1 mole of NaCl. Go to the periodic table, add up Na plus Cl. It's 58.45 grams. Multiply across the top, it comes out to be 1,899.6 grams of NaCl. Number 9. how many milliliters of water do you need to make a 1.5 molar solution with 46 grams of Ki? I'm going to use my little chart here because it's asking for milliliters, which is closely related to liters. So I'm going to need to do moles divided by molarity. Well, I don't know how many moles I've got, but I do know grams. 46 grams of Ki. Let's convert this into moles. So I'm going to get out my periodic table again and add up K plus I. That adds to be 166 grams. So I've only got 46 grams. This means I only have a fraction of a mole. 0.27 moles of Ki. That's divided by 1.5 moles per liter. That's going to give me how many liters I've got. 0.185 liters. Now to get that into milliliters, I need to multiply by 1,000. So I need 185 milliliters of water to make that solution. So what I would do then is I would take 46 grams of Ki, I would weigh that out on the scale, and I would add it to that much water, and then I would have a 1.5 molar solution. Technically, I would add a little bit of water and I would fill up to the 185 line, just for the record, for getting specific. What happens to the number of moles of solute when a solution is diluted? Well, let's test it out. So here I've got a beaker. I've got, let's just call it 3 moles. Okay, each one of those represents a mole. Now I add a bunch of water to it. Okay, I still only have 3 moles. It's just now they're spread apart more. So the number of moles stays the same. This was a trick question. Number 11. How many milliliters of a concentrated 3 molar salt stock solution would be needed to make 225 milliliters of a 0.5 molar solution? And how much water would you need to add in order to dilute this solution to make the right concentration? Ugh, sounds overwhelming. Not when you've got the dilution formula. So M1 times V1 equals M2 times V2. My stock solution is 3 molar. I'm going to figure out my mystery of how much I need to have for my total volume, because I want to make a 0.5 molar solution and I want to make 225 milliliters of it. So I'm going to get V1 by itself. I'm going to divide both sides by 3, and V1 comes out to be 37.5 milliliters of stock solution. So I've got a 225 milliliter volumetric flask, and I'm going to put the really concentrated stuff in the bottom, exactly 37.5 milliliters of it. Then I'm going to fill to the line with water, and when I shake it up, now it's diluted to that 0.5 molar concentration. So how much water did I add? Well, 225 minus 37.5, I wouldn't have to measure this out because I could just fill to the line, but for the record, I'd be adding about 187.5 milliliters of H2O. Another dilution one. If you see dilution or dilute, then you know what equation you're using before you even read on. It says you want to dilute a concentrated solution of HCl and take it from being 10 molar to 6 molar. So we're starting with a stock solution of 10 molar, and we don't know how much of this we're going to have to add, but we need to dilute this and make it 6 molar, and we want 750 milliliters. So I'm going to divide both sides by 10 to get our question mark by itself, and our V1 comes out to be 450 milliliters. So what that means is I'm going to have a volumetric flask where the line is at 750. I'm going to put in, it's kind of a lot on this one. This is my really concentrated stuff. I'm going to shade it in. 450 milliliters of the 10 molar solution. And then I'm going to fill the rest of the way with water. And when I shake it up, this whole thing becomes a concentration of 6 molar. You then measure 250 milliliters of the diluted solution from number 12 and add another 450 milliliters of water. What is your new solution's concentration? Okay. Again, it's another dilution. I'm adding water, so that tells me I need to use the dilution equation. So my stock solution is 6 molar. I'm adding, let's see, I've got 250 milliliters of this. I don't know the new concentration, but the new volume, it was 250 milliliters, but now I'm adding 450 milliliters, so that comes out to be a total volume of 700 milliliters. So that's my new volume. So I'm going to get M2 by itself. I'm going to divide both sides by 700. My new concentration, which makes sense because it's not 6 molar anymore, it's much more dilute. It's 2.14 molar. What is the significance of double arrows in a chemical equation? They show that the reaction is reversible. It can go both ways. A lot of reactions can do that. So putting a stress on a reversible reaction like this that's at equilibrium is going to cause a shift, either causing there to be more reactants formed or more products formed. So for example, let's look at letter A together. If you add a whole bunch of Cl2, all of a sudden this reaction is going to try and get rid of it because everything wants to balance out. It's like, oh my goodness, we got to get rid of this. So it will shift left is the wordage that we use for that. It will start producing more reactants. If you increase the pressure, that affects gases the most. So let's take a closer look. On the reactant side, there's 1 gas. On the product side, there's 2 gases. So these are going to all of a sudden be more affected. They're going to be colliding more and causing this reaction to shift left. What if you take heat away? You cool this down. All of a sudden, this side is going to say, where's our heat going? We need to make more heat. So it will shift left. What if we start removing PCl3 right here as it forms? The reactants are going to be like, oh my goodness, we need to make more of it. It's disappearing. So this reaction will shift right, just when you thought all of the answers were going to be shift left. All right. Hopefully that helps you through that Unit 6 quiz. And also I recommend taking the practice quiz and coming to one of the review sessions. All right, good luck.